Correct then. Yeah.
Right, let's start at the beginning.
Okay.
Okay, well, first of all, an introduction, and sorry for this. This is must be EMC. Very well welcome to this short webinar. Apologies for it being late. It's on EMC and railways. And my name is Stuart Charles, as some of you may know, and I've been working in the EMC arena for some 43 years, a hell of a long time, really providing EMC design input and latterly consultancy. So I've been working with Intellex to produce a novel EMC course. And what do I mean by novel? Well, this course, EMC application on railways, the thrust of the course is to provide non-EMC engineering staff and management actually with core EMI, electromagnetic interference, EMC, electromagnetic compatibility, design and installation design knowledge. Now, EMC courses are taught with maths, and I love maths, but I'm not a great believer in using it as a teaching tool. It just doesn't work. People go to sleep naturally, you know, who did maths when you're at uni. So we use animations, and together with an EMI demonstrator, as you'll see shortly, and 42 years or 43 years of raw EMC knowledge from myself. And I say raw because I've had a few bumpy rides in EMC, but they all add up to good experience. Now, there are a few formula in our course, but they're thrown in for good measure. And the course will be valuable to engineers, I guess, also, you know, to people who've just entered the field, if you've been in EMC for a while. But as I say, the course goal is to enable all engineering staff working in a railway environment to understand their role in EMC and to be able to dialogue with those unusual people called EMC specialists. And they talk in an esoteric language, which is actually unraveled in the course. You'll all know how to speak EMC at a very good level, actually. So the webinar, let's move on quickly as we're running a few minutes late. Now, the structure of the course is on EMC application in railways is, we're going to go through that now. After this, if you hold that slide, Rishi, please, we're going to look at some animations that are in the course. Two short videos on electromagnetic interference coupling in system cables, obviously with a demonstrator. And variable speed drives, something I've been working on for a few years. And if these aren't installed correctly, as you'll see, they can cause major issues. So that's a speciality that we'll only briefly discuss. We do discuss in detail. Basically then a short case study between apparently anecdotal interference between a TI-21 track circuit and a TPWS, that's train protection warning system, another system I've been working on. This is safety critical, so we'll take a quick look at that. So let's start with Rishi's first slide. This is the oh, sorry, Rishi, back one, please.
Oh, okay.
If you would be so good. This is the core EMC module, and I'll only quickly go through this, an overview, and the thrust is to give you really good knowledge, bring you up to basic EMC engineering level. Where are EMI sources on the railway? How do we test for them? Do we test for them properly? Subject I'm not so keen on, there are too many. EMC standards, but contractually you need to know a bit about those. EMC terminology. People talk about volts per meter in EMC, everyday terminology, and people go, volts per meter? Well, I understand volts, but I can't get my mind around that. So this is not mathematical, but we give you a good concept so you can relate volts per meter as a physical quantity. Coupling mechanisms, the Achilles heel of EMC, or that should be EMI, by the way, EMI coupling mechanisms. Waves and shielding. In this course, we take pictures. I have what I call a magic camera. We take pictures of waves. And back one, please, Rishi. Thank you. I'll let you know when to move on. And we look at them, how they travel down cables, how electromagnetic waves couple onto cables. As long as you know the physics, you don't need to know the maths. Fourier analysis, again, a very important subject, as we'll see with some videos shortly or animations. And power quality. Power quality is quite an important factor if you actually contaminate the mains. Certainly in the UK, I'm not too sure about Europe. You have to meet G5/4 because you can cause EMI with other users. Very key, how do you install a station, maybe a railway, to ensure it meets EMC? So real installation design knowledge and EMC management. Could we move on, Rishi, please? Next slide.
Yeah.
Okay. I think there may be another click on the button there, because that's the one. The basic EMC course, which we've just discussed, has now been basically enhanced with a number of packages. Number one on the left, how does EMI actually couple in on the railway? How does it get into cables? How do you screen cables? We'll look at that again. So this is really fundamental stuff on the railway track and in stations and possibly in rolling stock. Number two, I don't know how many of the audience know how to read a spectrum analyzer. You may never need to use one, but they are useful for demonstrating electromagnetic interference coupling, how you should and should not ground cables. We'll see examples of this. And so we do look very briefly how to read one. You may never need one, but if you know how to interpret it, you'll also know how to understand filtering results. Right. Rishi, could you just turn back once, please? Thanks. I'll flag up when we need to move on.
Yeah. No, it's actually automatically moving. That's a problem.
Okay, no problem. Number three, a favourite subject of mine. What do you do with a screen cable? Do you screen one end? Do you ground one end? Do you ground both ends? You have to ground one, otherwise it won't access the screen. And then you have the infamous pigtails. Sometimes you get braided shields, foil and braided shields, foil and braid with a pigtail, braid without a pigtail. Are pigtails good? And how should you terminate a cable? All very important for EMI. And there's too much anecdotal information in the field. We need the real answers. So that's what we look at. Could we move on to the next slide, please, Rishi?
Okay.
Okay. I've been working for 6 months with a company, major company in the United Kingdom, and they had some problems with an RS485 link. So this is a high-speed differential pair link. And the problem is, how do you ground the screen? And how do you ground the transmitter and the receiver? This could be a 60-meter cable, or it could be a couple of 100-meter cable. And there could be daisy chains, a transmitter talking to many receivers. It could be a building management system. It could be many, many things. But how do you install it to avoid EMI? And there's some very good things that come out of that. Do mains cables cause interference? People say yes, others say, well, not too sure. But what we do is, from any of you remember Ampere's law, could we go back, please, Rishi? Thank you very much.
Okay.
We uncurl Ampere's law, and we get some very interesting results about power cables coupling into signal cables, not public domain. So that's new. Never seen this. We also talk about filtering, and we need the spectrum analyzer, which is a graph at the bottom right of the screen, to basically look at what happens with filtering. So that's why we need to understand spectrum analyzers. That's a standard Schaffner filter used in Crossrail quite a lot. And that's the chart there of how well it filters, which we'll talk about later or another time. Then there's something I really like. I'm very keen on the power of association. So TOOF, it's an acronym, and it's mind-bending. If you understand this, you will understand so much about electromagnetics in the real world. A very quick story, and this is the association bit. My father-in-law was a Cockney. That means he was born in the East End of London near Bow Bells. That's the definition of a Cockney. A very quick story for the association part. The two Cockney chaps talking to each other. One's called Harry, the other's Joe. And Harry says to Joe, "Hey Joe, how are you today?" And Joe says, "Oh, I'm not so good, Harry." And Harry says, "Oh, what's the matter, mate? What's the problem?" And Joe says, "I've got a bad tooth. I've got a bad tooth." Right? Dentistry. Now, the power of association here. You should always remember that crazy story told to you by apparently an EMC engineer. Now let's look at the acronym, because this is so powerful. This was an electromagnetic epiphany for me. It opened my mind. TOOF stands for the Theory of Orthogonal Functions. Some of you may have come across that, but this is so powerful, again with no mathematics, because it tells you two things. It tells you why mains harmonics, current harmonics essentially, do not contribute to real power in the load, and they cause overheating in transformers and cables. And for electrical engineers designing systems, they need to understand that. But more importantly, this horrific Fourier transform, Fourier series, discrete Fourier transform, fast Fourier transform, all this stuff about turning waveforms into sine waves, it explains how a dumb computer does this without any maths. No integrals and e to the j omega, none of that stuff. This is just simple maths with a few with a few graphs, and basically all you need is high school maths, which is multiplication, addition and division. This is really powerful, and we discussed this on the course. It will change your electromagnetic life. Could we take the next slide, please, Richie?
Okay, yeah.
Okay, this is the demonstrator you'll see using some videos very shortly. Basically, it's a large board. It's meant to emulate a station. Obviously, the geometries are much smaller, but nevertheless, you know, frequencies carry through on distance. And what we've got there is a little ground plane at the back of the demonstrator. You can see it's a brass ground plane. And we've got some cables connected from the left-hand bracket to the right-hand bracket. Cable 1, cable 2, you can see, and we'll see these in the videos in a bit more depth. And the idea here, oh, by the way, we've got another earth. So that large ground plane earth you see at the back has got a parallel earth, a very thin one, which we're going to emulate, and we're going to call a station earth. This is a station earth as against an earth between two bits of equipment, one at one end of the red cable and the other at the other end. So we're going to use this in some videos very shortly. So we'll move on to the next slide. Now,
Okay.
what we do a lot of mind experiments. I've updated my slide pack, and it's a shame we've got some computer issues at my end, but essentially we're going to look at what happens when a wave. Rishi, is a couple more clicks on that slide, I do believe.
Okay.
Yeah, we've got
Yeah.
Thanks. We've got a 10-meter cable, and you're now watching the video, and it's a wave. We're watching a wave travel down a 10-meter cable. This is EMI. It's not a wanted signal. It's an electromagnetic interference signal. We're wondering what happens, because this is what happens in the real world. That's been picked up probably from free space, or it may be coupled on from another cable, and it's reflected at the end because EMI signals are not matched. Unlike twisted pair, where we have a nice 120 ohm termination for high-speed data, these aren't matched. Now, the red dotted curve is the composite of both of those forward and reflected waves. Then we've got a green wave coming back. And essentially, we can see we're getting a standing wave set up, and a standing wave will radiate because current produces electromagnetic radiation. And this continues. And if you like, Rishi, you could speed along the bottom and go to the end of that. And that's great. That's great. And there we can see we've got massive resonance, and we get massive interference coupling both to adjacent cables and re-radiation. So this is the type of teaching methodology we use throughout the course. And so there's no maths there. If you go into transmission line theory, which I had to do to produce this, you just get bogged down in mathematics, and that's not the objective of the exercise. Okay, Rishi, could we move on, please?
Yeah. Yeah.
Thanks very much. So Jean-Baptiste Joseph Fourier, one of my sort of electromagnetic heroes, although he wasn't involved in EMC, son of a tailor, and he was a French mathematician and physicist. This chap died in 1830, went to Egypt with Napoleon, and this guy put the foundations for Fourier analysis. And we're going to talk very briefly. Essentially, the thrust for EMC, not for high-speed data transmission, but for CMC, is that any waveform that's being transmitted by radio wave and or over cables or the mains, any current traveling down mains cables, any waveform can be decomposed into sine waves and cosine waves. And who cares? Well, the key thrust here is for EMI Each one of those waves, which are of different frequencies, and we'll see a video on this or animation, could cause EMI, especially in variable speed drives. So, okay, this is a rerun basically of adding together a number of sine waves, and you can see we're forming a square wave. Amongst friends, it's a square wave. It's not a very good square wave, but we'll take a look at the next slide pack in a second. Could we move on to the next one, please,
Yeah.
Richard?
Okay.
Yeah. Okay, and now you'll see we're adding together a very large number of sine waves, and you notice we've got a perfect square wave. Now, there's a bit of my wife says I'm a magician. I have a bit of English humor, very basic. I have a habit of basically disappearing at strategic times, like when the grass needs cutting and we've just eaten, you know, we've got to wash up. Well, my eyesight's so bad that I'm very good at washing up, but there's some trickery here, and I'm not going to tell you what it is, but if those of you want to look up I think it's Josiah, J. Willard Gibbs. Now, he was, I believe he was a mathematician, as a scientist involved in physics, chemistry, and maths. And he came up with something called Gibbs phenomena. If you've done Fourier at university, you'd note that. So there's a bit of trickery in that waveform. Let's move on. Okay, in this video, we have an Agilent, or Keysight as they are now, 33600 series waveform generator. It's sweeping in frequency, as we saw before, this time from 100 kilohertz to 80 megahertz. Now, the output is actually fed into our EMC demonstrator in the red wire. There's a 50 ohm load at the end, so current goes down the red wire, through the load, and returns through the ground plane back to the outer of the coaxial feed. The black wire is not connected. It has a 50 ohm load. It's adjacent to the red wire, and we take that output into the spectrum analyzer. Now, at the moment, the black wire is disconnected. We have 100 dB microvolts at the top of the screen, and we are about 8 boxes down, 80 dBs, leaving 20 dB microvolts, or in friendly terms, 10 microvolts. dBs, there will be a little chart if you're not familiar with converting decibel microvolts to microvolts. Okay, I'm now going to connect the signal wire so that we can now get a signal from the black wire, and let's have a look on the screen. That's a spectrum. Now, what we're seeing is a number of frequencies. As the signal generator steps in frequency, the spectrum analyzer, which is sweeping, captures each frequency. You can see at low frequencies, about megahertz, the box goes from 100 kilohertz to 100 megahertz. We're getting very low pickup, crosstalk as it's called, and it's increasing up to about, let's say 10, 20 megahertz, then decreasing a bit. We'll look at that later. And my sig gen only goes, this chap only goes up to 80 megs. That's why we don't see any frequency spectrum. So that's first indication of crosstalk from a swept sine wave that's emulating electromagnetic interference. We're getting system coupling between cables. In the next part of this crosstalk experiment, we're going to look at what happens, and this is a key factor, when you run cables close to a ground plane. Now, in an installation, a ground plane could be a cable tray, could be trunking, but let's take a look. Now, what I've done here is to drop the red wire much closer to the ground plane, so the current now has a return path much closer to the red wire, and the black wire is also on the same spacing but much closer to a ground plane. Now let's switch on the trace and see what happens. Hopefully the crosstalk will drop. You never know in these experiments, maybe I've done something wrong, but let's take a look. Okay, we're going to max hold, and there we are. That's pretty graphic, right? So the crosstalk onto the black wire from the red wire has dropped, well, certainly I would say, couple of boxes, so 20 dBs, 10 times. That's radical. So this is a very key point when designing installations. Cables that are not run close to a ground plane will produce crosstalk between the culprit and the victim much greater than if the two cables were run over or close to a ground plane. A very key fact. Now at the end we can see these strange resonances. That's due to the length of the structure, and we do discuss resonance later on. In this video we're looking at a true or simulated with the Keysight 33600A series waveform generator, an AC PWM signal. Again, as always, we're passing into our red lead and we're measuring the current on that red lead, and you can see that the current, for every microamp we get a microvolt. There's nothing there, and that's because I need to put a load on the cable. So let's put our 50 ohm load onto the cable. We should now see some current because the current's going down the red lead through the 50 ohm termination back to the ground plane. So let's take a look, and there indeed is our spectrum of current that's passing through from the VSD simulated output to a variable speed fan. So we'll now max hold that, and what we're going to do now is measure the current, the contaminated current that's flowing through the external system earth, this earth here. Because if we do get current flowing through that earth, we've really lost control of our electromagnetic interference, or we could have if we have a poor installation. So I'm just going to turn this video off for a second. Okay, I've now moved the current probe from the simulated VSD output to the main station system earth. See how much contaminated current our drive is dumping into the earth system. I now need to switch on trace number 2 and clear write the screen, and we'll get a blue trace. There we go. So you can see there's still a fair bit of current. Let me max hold that. A fair bit of current flowing into the external earth. We're about what, 1, 2, 2.5, 2.25 boxes down, 20 dBs. Our external current that should flow back through the VSD SWA or local earth, a tenth of it, 20 dBs is 10 times, a tenth of it is still flowing through our external earth. So now we're going to look at how we can prevent that from happening in the next video. This will come on in a few seconds. In part 3 of the video, what we're now doing is driving our simulated VSD output down a screened cable. It's the 50 ohm termination. So the current is flowing down the center conductor of the coax and returning through the braided screen. And again, we're looking at how much contamination in terms of current flows through the external system earth. So again, I need to go on to trace number 3, which I'm already on, and I need to clear write it, and then I'm going to max hold it. Now you can see that effectively above 10 kilohertz, 20, 30, 40 kilohertz, there's negligible current now in the external system. Now we could find, if we disconnect the current probe, which I'll do shortly, that trace stays much as it is. In other words, we're at the system noise floor. Let's do that to see if in fact we do have any external current. The probe will hopefully come off. Always difficult when you're doing live videos. There we go. So we're not measuring any current now, but have we got the same reading? We have indeed, and let's max hold that and view it. So basically we're measuring noise floor of the receiver. We cannot see any external contamination of current when we're using a screened cable. Now in the real world, your drive, your VSD output, the 3-phase motor, will be probably 3-core cable with steel wire armor. But the key thing is the SWA must be terminated at both ends. Otherwise, we will not gain this reduction in external noise. That's not the whole story. We yet have to talk about filters, because we can still be contaminating the mains, dependent on whether the VSD has an input filter with its 3-phase 50 Hz supply, and how we design our AC switchgear. That's in another section. So if we go on to the last slides now with the pardon me, TI-21 and the TPWS, we can look at that. So this is a purported case study between 2 track circuits. I was lucky enough to work on this. Now, there was anecdotal evidence that the TI-21 track circuit, which we'll look at briefly in a second, produced frequencies that interfered with TPWS. TPWS, there's a train stop when you have 2 grids together, and a train break when you have 2 grids apart. Those 2 grids have literally just coils of wire in, and we pass a current through, and the TSS, the train stop, radiates a magnetic field upwards from the 2 grids at 2 different frequencies, 66.75 and 65.75 thereabouts kilohertz. The overspeed sensor basically has 2 grids, and again it operates at very similar frequencies, as you can see. And the idea there is the train receives a signal. This is the receiver on the train. The train receives a signal. It's a magnetic field that's changing, and it produces a voltage in the train. So the train senses a signal from the loop. With the OSS, the time between the 2 grids, that's measured, and the velocity of the train is calculated. So if you're coming up to a limited speed area, the brakes will be applied if you're going too fast. Okay, Rishi, if we could take the next slide, please. That would be great. Pardon me. So here we have the TI-21 track circuits frequencies, the nominal fundamental frequency. And you can see I've circled 2, 1996 Hertz, 2593 Hertz. Now these are square wave drives at pretty large voltage. And as you're seeing, a square wave is actually composed of a series of sine waves, and each of those could cause interference. And that was exactly what was happening in this purported, I say purported or anecdotal evidence that the TI-21 interfered with TPWS. TPWS did pick up a spurious signal, and this was one of the original views that this could be the source of EMI. Could we take the next slide, please, Richie?
Okay.
Now, the concerns were that the 25th harmonic, so 2,593 times 25, because we've got a square wave and it's got all these frequencies, or the 31st harmonic of 1996 could cause enough rail current to falsely trigger TPWS, Train Protection Warning System, and be recognized as an in-band signal. EMI, you know, could have an accident on the train, braking or whatever. So what we did, I actually worked with the designers of the TI-21. We did a Fourier analysis. We worked out the size of the voltages of the various harmonics of that square wave. And we did some analysis, which we don't even need to go into, of the impedance of the railway tracks and the load, the TI-21 transmitter and receiver. We worked out the current that's flowing in the railway from the TI-21, out of band current. The next slide shows, okay, no, we're ready to roll there, Rishi, thank you. What we do, simple bit of mathematics to work out a current in a wire, or in this case, a rail produces a magnetic field. Each rail contributes. We know that TPWS will not sense below 60 nanotesla. That's a magnetic field strength. Don't have to worry about that too much. And we worked out you needed 100 milliamps to produce that level. So, you know, could this be the issue? And a simple bit of maths. If we go to the next slide, Rishi, please.
Yeah.
Now, what we found was that current would needed to actually cause false triggering or a false signal on the TPWS was 33 times lower than the minimum threshold of the TPWS. So it could not have been a problem. So we had to move on. And the issue was actually traced to a faulty component on the TPWS board. There were about 2 boards with a faulty component from the manufacturer. They were out of spec and they caused, we analysed it. We did a root cause analysis. We undertook a root cause analysis and found this was the cause. However, the anecdotal evidence, I guess, still stands amongst the people who were not involved with this. But it does show you how EMI could theoretically, unless you go through quite a detailed analysis, affect different systems. And of course, this is safety critical. Okay, Rishi, that's the course. If anybody's got any questions, you could perhaps raise them now, or you could certainly email Rishi for my attention. So it's over to you, good people.
Yeah, Nazim's hand is up. Maybe you can start with Nazim.
Thanks, Rishi. Thanks, Stuart. That's a good presentation. I was going to ask you a question earlier on, but you've answered it in the last slide about a real EMI concern with regard to the railway environment, and you've done a quite nice example there. But then your root cause have then concluded that it wasn't anything to do with the track circuits, but more to do with the system component itself, which is also equally interesting. But I just wanted to ask, I mean, by the way, I've worked with Rishi and Madeline for a good few years now, so and we're safety engineers, and we've very much identified EMI as a source risk, and we look to designers implementing EMC components. So have you got any example of real risks to the railway in terms of wrong side failure that warrants the design against the relevant standards?
Well, I guess,
Stuart, sorry, just to give you, sorry, it's Mel.
Yeah,
just to give you a hi, just to give you a clue. I know when we got you to do some work maybe 20 years ago, you did some very good work where with the help points. I don't know, you may want to use that as an example where we had concerns about the help points working, affecting the deltas.
Yeah, that was a very interesting one. We had some deltas. Yeah, this was when I was a young man, right?
You were a lot younger.
Yeah, I mean, Mel's raised a good one there. So I was tracking back to think of some. So on the Victoria line, we had a signaling system where there were tones generated. The tones were generated by, this was track to train, and the tones were generated by a number of coils that produced a magnetic field. It was the same sort of signaling as we saw in TPWS. I remember one of the communication engineers calling it the Victoria line jangles. I said, why do you call it that? And he said, well, the telephone lines are picking up all these different audio frequencies from these loops. Okay, but the issue was they were quite concerned. We were concerned that help points for people with impaired hearing could actually be degraded, and in fact, if there was an emergency on the station and there was a help point and somebody went to it with impaired hearing, they wouldn't be able to basically decode the audio because there'd be so much noise. And this is obviously dependent on the design of the help point, its co-location to the track, is it near a loop, and various other things. So that was an investigation, and thanks for bringing that up, Mel. I think we concluded that if the help point was situated in the correct place, then the audio breakthrough into the magnetic loop that, of course, would pick up noise from the magnetic loop on the Victoria line. The fall off of the magnetic field was such, I think it's 1 over d squared with d as the distance, as I recall, without checking my books. It was okay if it was installed in the right area. So it's a very good point you brought up there, Mel, and thank you for that.
That's great.
The interesting thing, Stuart, if you remember, at the time we were upgrading a lot of stations, and the help points, I didn't realize were made by one manufacturer, and we were reliant on this one manufacturer. They have huge audio frequency induction loops in there. Our concern, the whole point of the investigation, was to look at the effect the railway had on the help points. And during that investigation, Stuart pointed out that, hang on, we are focusing on the effect it may have on the audio frequency induction loops and, impaired hearing. But the concern was actually the other way around. And so often it happens where we are, especially in an investigation, we're so focused on looking at one aspect. But most systems, there's a process of reciprocity. A system can interfere with once, when you're looking at what's an effect, it could be the other way around.
Yep.
No, I thought I'd just bring that up because it's one that stayed with me for a long time.
Yeah, I mean, very interestingly, I don't know if anybody else, say yes if you have. Has anybody been involved in, I'm not going to mention names or projects, in a variable speed drive issue in the last 2 years?
Yeah, I have, Stuart, and we can share that sometime together.
Yeah, I mean, we can't talk detail, but one of the reasons I've been looking at VSDs, and unfortunately, because you didn't get the slide pack, ladies and gentlemen, there's some really interesting stuff about how variable speed drives, this is large ones, if the cable's too long between the variable speed drive and the fan or the variable load, or you don't screen it properly, or it's a very heavy duty load, or, and this is very interesting, so I've been researching this after the issue was, inverted commas, closed out, or if you don't design, and this is bizarre, if you don't design your switchboards correctly, people are going, what? Yeah, that's what I'm coming up with. If you don't design your switchboards correctly, you could actually produce, or you could not suppress. You can cause more EMI with variable speed drives than if you didn't know. If you didn't know about this phenomenon, you'll just design your switchboard. But you need to think about large VSDs when you design it, how you earth it, and that's in the new slide pack, and that's why it's so key to move on there.
That's right, Stuart, and I think one of the things is most electrical control systems are becoming more complicated. They rely on microprocessors. They have a lot of electronics in them, so these things are more vulnerable now to noise from various drives, etc.
But certainly from my side, the key thing I want to do, having been 43 years in electromagnetics, I mean, gosh, that's a long, long time, is to really pass this knowledge on, because I think we can actually engender such information in non-EMC people that they'll understand most of the risks, and then, hey, life's going to be so much easier, and that's the thrust of the course, really. Has anybody else got any questions they'd like to raise?
Stuart, I'd just like to thank you for finally explaining to me what the standing wave stuff is all about.
Oh, right.
I first came across that from a lecture in a university. Oh my goodness. Well, this would be 40 odd years ago, but anyway.
Right. Well, no problem, Madeline. Thank you so much. I mean,
basically that on their lab bench, they'd managed to blow up some waveguides with a standing wave. I thought, how on earth could you actually produce enough energy to damage something physically?
Yeah, it's all to do with reflections. Yeah. You're right there, Maddie. I mean, depending, I showed a short circuit load, so we saw current going to zero there. If you've got an open circuit load, and this is EMI, so you'll terminate electromagnetic interference generally, you get double the voltage, and then you can get all sorts of nasty things happening. And the key with that video was a standing wave. It's current that causes far field radiation, and you've got a standing wave on the cable due to resonance. You wouldn't know about this. You just know that you had an enhanced EMI problem at a particular frequency if you investigated it. Yeah, so it's a bit of a minefield of
yeah, I think Stuart, that was a good picture that you showed up, Stuart. And for those civil engineers on the line, you all know what when you're building bridges, you don't want to get a resonance.
Absolutely.
And it's exactly the same thing. It's exactly the same thing.
We're talking about electromagnetic resonance. I mean, as I recall, I was told by my father that soldiers many years ago used to break step going across a bridge. so you don't resonate the bridge or the structure at its resonant frequency.
We, all these years and all the lessons learned, we still got it wrong with the Millennium Bridge.
No,
Because-
yes, apparently. Oh well, it's tough. Engineering is a tough field, isn't it? But it's a very rewarding field once you get to understand things, And so again, I will just say once more, I'm so much more material I wanted to show you that wasn't in this slide pack, because Rishi has my early one and it's been upgraded now to version 4. And I do hope that if a few of you are interested, because there's some good stuff in there, basically you would seen the effect of the screen cable, which wasn't in this particular one, terminating the screen at both ends, which you only do on certain times, not every cable. So yeah, I do hope we can rerun that, and there's a chance this next time to do that. But yeah, well, thank you everybody for your time and for attending.
Stuart, can I just say something before?
Yeah,
please.
Before you close off. I think first of all, I want to say what a great presentation that has been. And I've known Stuart for a long time, and he's been doing EMC for 3 months longer than I have, and he knows why. He got on this planet 3 months before me.
That makes you a young man.
We've the other thing that I took from what Stuart was saying, he's getting to a stage now where he feels he wants to impart that information across to as many people as he can, because it's a very plausible thing to do. The other thing that came out from your presentation, Stuart, is it's as much a science as it is an art, and the art of EMC and knowing what to look at or what to look out for. And that comes from just experience, I guess. So yeah, that's all I want to say, Stuart. Thank you very much.
Yeah, thanks, Mel. Thanks for the feedback. Appreciate it. Oh, well, by the way, I was going to say, you may not all be here. I was going to say hello to Nigel, a few people: Nigel, Harry, Paul, Josh, Dave, Ben, Buchanan, Henry, Hamber, and I think Harrison. I've met a lot of you guys but a long time ago, but good luck with your EMC hunting, ladies and gentlemen.
Thanks, Stuart.
Intellex Training courses. Intellex is starting new batches for the Railway, Rams and System Engineering courses for the academic year 2022 to 2023. Intellex is a registered member of continuing professional development body, the Training Course Certification Body in the UK. All Intellex courses are certified by the CPD. Module level courses. These courses cover each discipline in depth. This is of interest for those who want to develop their skills in specific disciplines. The module courses are available for System Safety, RAM, System Engineering, and System Assurance disciplines. Certificate course in Railway, Rams, Concepts and Applications. This is the most popular course where it covers System Safety, RAM modules, and also some chapters from System Engineering and System Assurance, which are essential for the application of RAM's concept. Certificate course in Railway, Rams, System Engineering and Assurance. This course covers all disciplines in detail, followed with a coursework based on tasks encountered in a real-time project. Advanced Certificate course in Railway, Rams, System Engineering and System Assurance. This course is suitable for the participants who aspire to practice as a system engineer or RAMS engineer. The course covers all elements of the certificate course in System Engineering and RAMS, and in addition there will be a 1-week case study based on typical systems RAMS project. The Advanced Certificate course is certified by the IRSC UK. EMC Overview course. This course familiarises you with EMC concepts and its applications in the railway. Appreciation course. This course is suitable for senior managers and engineers who like to have an over-familiarisation to railway RAMS, system engineering and system assurance concepts and application, as nowadays RAMS delivery and performance is commercially important and attract penalties. Customisable course. Apart from the standard courses, Intellex can customise the course content to your requirements, which are available for corporate training. For further details, contact training@intellexservices.com.